Hi everyone, myself D. Mohanraj, working as Assistant Professor in the Department of Mechanical Engineering, Adhiyamaan College of Engineering. In this video, I am going to explain the shape function derivation of linear one-dimensional bar element in finite element analysis. One-dimensional element. So this one-dimensional element is also called as an line element since these elements are used in one-dimensional problems. And some of the one-dimensional elements which are shown here. So in the first one, the line element which has two nodes, and it is also called as an linear bar element since it has only two nodes. And the second one, it has three nodes, and this element is called as quadratic one-dimensional bar element. And the last one, it has four nodes and it is called as cubic one-dimensional bar element. So here the variable will be in only one direction, either along the x direction or y direction. So these elements which are suitable for axially loaded problems. And to obtain the shape function of the linear one-dimensional bar element, or it may be an quadratic one-dimensional or cubic, the polynomial equations are best suitable for the shape function derivation due to its differentiation and integration of polynomials which are quite easy. Also, it is easy to formulate and computerize the finite element equations. Due to these reasons, these polynomial equations are preferred in obtaining the shape function. And the general form of polynomial equation is shown in equation 1, that is u of x, which is equal to a1 plus a2x plus a3x square plus a power x power 4 up to an x power n minus 1. Suppose if you are going to obtain the shape function for two-noded bar element, then we have to select the linear polynomial equation, that is up to a2x. That means the order of the polynomial should be 1. And if it is in the case of quadratic one-dimensional bar element shape function, we have to go for quadratic polynomial equation, that is up to the third term, that is a3x squared. Up to that we need to select the polynomial equation to derive the shape function. And if it is in cubic, we need to select the cubic polynomial equation, which is up to a4x cube. So now let us start the shape function derivation of linear one-dimensional bar element, or also it is called as two-noded bar element. Let us consider a bar element with length L and nodes 1 and 2 on either end of the bar element as shown in figure, with the nodal displacements at node 1 as u1 and at node 2 as u2. Now the coordinate at x1 is equal to 0 and at x2 is equal to L, because it varies from 0 to L. Now we need to choose the displacement function, which is represented by u here, and this u will give the axial displacement, that is throughout that element length. And here we are going to choose the linear displacement model, and for that we are going to use the linear polynomial equation which is shown in equation 1, that is u of x is equal to a1 plus a2x. So the order of the polynomial here, it is 1, and this is called as the linear polynomial equation. And we are going to name it as equation 2, and this equation 2, if we are going to write it in a matrix form, we are going to get u of x is equal to 1x and a1 a2, that is a row matrix and a column matrix with the order 1 cross 2 and 2 cross 1. Now at node 1, the x is represented as s1 x1 and u is represented as u1. Similarly, at node 2 x is represented as x2 and u is represented as u2. Therefore, if you substitute these coordinate values and the displacement field in equation 2, we are going to get u1 is equal to a1 plus a2 x1 and u2 is equal to a1 plus a2 x2. Now if we write the two equations in matrix form, we are going to get the matrix which was given by equation 6. u1 u2 is equal to 1 x1 1 x2 multiplied by the vector a1 a2. So here we need to find out the unknowns, that is a1 and a2. So for that we need to substitute the coordinate values at node 1 and 2. So at node 1 the x1 value is 0 and at node 2 the x2 value is L. Now we are going to substitute these two in equation 6, and the equation 6 will be reduced as u1 u2 is equal to the 2 cross 2 matrix with 1 0 1 L multiplied by the unknown vector a1 a2. And our aim is to find out the unknown vector a1 and a2. So if you have taken the 2 cross 2 matrix to the left hand side, it will become inverse. So we need to find out the inverse for the 2 cross 2 matrix, which was shown in equation 8. And let us take that 2 cross 2 matrix in equation 7, that is 1 0 1 L, as C. So that is the connectivity matrix which can be taken as C, and we need to find out the inverse for that matrix C. And the inverse for the matrix generally is given as adjoint of that matrix divided by determinant of the particular matrix. So the adjoint is nothing but the cofactor of that matrix transpose. So with this formula we need to find out the inverse of the matrix C. So for that first we need to find out the determinant for that C. So the determinant of that C will be given as L minus 0, which is equal to L, and the adjoint of C is given by 1 0 minus 1 1. Sorry, C is equal to L0 minus 1 1. Actually for 2 cross 2 matrix we can write the adjoint by interchanging the leading diagonal elements and by changing the sign for the other two elements. So that is the simplest method to find out the adjoint. Next to the C inverse, that is the inverse of the matrix C, is written as 1 by modulus of C, which is given by 1 by L, since the modulus is L, and the adjoint matrix is L0 minus 1 1. And I am going to divide all the 4 elements by L. So I am going to get 1 0 minus 1 by L and 1 by L. Now we are going to substitute this inverse in equation 8, and we are going to multiply that 2 matrix, or else we can directly substitute that a1 a2 unknown value in equation 3. So in equation 3 u of x is equal to 1x multiplied by a1 a2, it was given in equation 3. So in place of a1 a2 we are going to write 1 0 minus 1 by L into u1 u2. Now we need to multiply these 3 matrix, that is 1 cross 2 multiplied by 2 cross 2 multiplied by 2 cross 1. So the final size will be 1 cross 2. So after multiplying these 3 matrix we are going to get 1 cross 2. So first if we multiply the first 2 matrix, that is 1x and the 2 by 2 matrix 1 0 minus 1 by L and 1 by L, that is 1 cross 2 multiplied by 2 cross 2. So we are going to get the resultant matrix as 1 cross 2, which is given by 1 minus x by L into 1 minus x by L and the first row second column as x by L. This has to be multiplied with the displacement, nodal displacement vector u1 u2. So now we need to multiply this 1 cross 2 with 2 cross 1. So finally we are going to get 1 cross 1. That means 1 minus x by L has to be multiplied with u1 plus that x by L has to be multiplied with u2. Now this can be rewritten as u of x is equal to n1 u1 plus n2 u2. Here the n1 n2 are the shape functions, where n1 is equal to 1 minus x by L and n2 is equal to x by L. So by using this u of x is equal to n1 u1 plus n2 u2, we can find out the displacement at any point inside that element, that is between 0 to L. We can find out the displacement. So in place of x, we can substitute the value between 0 and L. If you know the coordinates, then length of the element as well as the nodal displacement. And the characteristics of shape function, that means the shape function value is 1 at its own node, that is at node 1 the n1 value is 1, and the node 1 value at, that is the shape function value at node 2 is 0. So that means the n1 is 0 at node 2. Similarly, the shape function value at node 2, that is the n2 is equal to 1 at node 2, but the n2 is 0 at node 1. That means the shape function is 1 at its own node and 0 at the other node. And the another characteristics of shape function is the summation of all the shape function are equal to 1. That means if you add the shape function n1 and n2, you are going to get 1. That is 1 minus x by L is the shape function 1, whereas x by L is the shape function 2. If we add these two, we are going to get 1. And the plots of shape function over that domain of the bar element is shown below. In the first diagram, the shape function value is 1 at the node 1 and it is 0 at the other node. So it was plotted in the first diagram, and in the second diagram at node 2 the value is 1, but at node 1 it is 0, which is represented by the shape function 2 with x by L. Whereas the third diagram, which shows the displacement at any point between that element, which is given by u of x is equal to a1 plus a2x. Thank you.